Let's get started. If you came in a little late and didn't get your exam, just grab it after class. Again, two parts. The last page is over here. All the front pages are over there. If for whatever reason it's missing or you didn't see it, please come talk to me after class and we'll go next door and see if we can hunt that down. I will be posting the exam solutions, so just look online, compare your answers to what is correct, or to confirm, you're like, yay, I did it right, this is fantastic. Look that over, and if you have questions, by all means, email me or ask on Thursday if something's not making sense, all right? We have 3 chapters remaining. It's not that bad. It's not just, hold on a second, it's not bad. So, chapter 32 is what you see being started here. There's some stuff that's in there. It's relatively short. There's how many slides? 7. So that's kind of okay. And then chapter 33, there are 7. And I'm not necessarily even going to cover all of them. Actually, in that one, I'm dropping 2 of them. So that's 5 slides in chapter 33. And then in chapter 34, well, there are more that are here. There's 15, but I'm going to drop quite a few of those as well. So in other words, we're probably going to finish 2 of the 3 chapters today because that's like 12 or 13 slides, which really isn't all that much. And then we'll finish up whatever's left over on Thursday. And then we'll be done with all the new material. And I should also tell you that that last chapter, chapter 34, is only conceptual and barely that. Okay, so there's not going to be like any problems of any type from that. If I remember correctly, there's not a homework assignment over that chapter. There's a chance I may ask you a multiple choice question about it, but even that would be about it. Okay, so don't worry too much about what we do on Thursday. Basically, all the new problem solving stuff that you may have to be concerned about happens today, and then we'll be done. Sound good? Yeah, you're like, no, it doesn't. 3 chapters. Of course, it sounds terrible, but they're short, so it's going to be okay. So let's start with this chapter 32, where we're going to continue some of what I talked about in the video lecture, which I hope you watched. No? No, not yet.
There's one thing, your students are honest.
I appreciate the honesty, I guess. So the basic idea, without going back over all of the details in the previous chapter, which was chapter 31, is that if the magnetic flux, or how much magnetic field is passing through a coil of wire is changing, it like magically produces a current in that coil of wire. Meaning you can have a circuit that's literally not connected to power in any way, and if all I do is maybe have a loop of wire somewhere in that circuit and a magnet, and then I change the magnetic field that's passing through that loop, all of a sudden charges start moving in that other circuit that's not connected to anything, which is kind of cool and kind of magical. All the details for how that works and how to solve problems with it, they're in the lecture online, all right? I want to extend that just a little bit with this first slide, and then we're going to kind of branch off from it just a little. So you'll notice in this diagram we have a coil of wire. We're going to assume it's like connected to something that can provide a current. You can see there's a current 1 that's going through the coil of wire, all right? If there's current going through that coil of wire, it's producing a magnetic field. So if I take another coil of wire and put it really close to that first one, well then the magnetic field that's being created by this one just happens to be passing through that one as well, okay? And keep in mind, this one's not connected to anything. It's just sort of sitting there, all right? There's no battery, there's no power source, there's no anything. Maybe these wires literally just go over here and just, come right back, okay? Maybe they're not connected to anything literally. So if this magnetic field is passing through this one, I only need to do one more thing, and that's change this magnetic field. If this magnetic field is changing, then the one that's passing through this one is the same one, and it's changing, which means you will spontaneously get a current that's formed in that second loop of wire, okay? This is, again, an extension of what was in chapter 31. So coming in from chapter 31, we have that. This is known as you can see up there, mutual inductance. Two different coils of wire. One of them, I have a current that I'm putting through, and if I change that current, it produces a current in another nearby loop of wire. We've got a couple of equations we can use to get to something for this. So first of all, let's see. I'm trying to decide how much of this to tell you and how much to skip over. Let's do this. Let me write this out first and then I'll explain it. N sub 2 times the magnetic flux sub 2,1 equals M sub 2,1 times I1. Let me explain what all of those things mean. And then you'll see that it's related back to this diagram that's over here. So this whole thing is the total magnetic flux through coil 2 that's coming from coil 1. The total magnetic flux through coil 2 from coil 1. So notice, flux sub 2,1, that's simply how much magnetic field is being produced that passes through coil 2. The N is just how many loops there are in coil 2. So if there's one loop, well, you just get one flux. But if there's two right next to each other, then, well, it goes through both of them, so it's just multiplied by 2. If this second coil has 100 little loops of wire, then you multiply the flux by 100. You've got 100 times as much magnetic field passing through, all right? How much magnetic flux you have passing through this coil relates back to how much current there is in the thing that's producing the magnetic field to begin with, all right? And those are connected by one additional item, which is a proportionality constant known as the mutual inductance. Mutual inductance. And let me just go ahead and put up here, this is the current in loop 1 that is producing the magnetic field. So all of the things that are actively happening are happening over in loop 1, and loop 2 is just sitting there sort of receiving, waiting. Things are produced in loop 2 as a result of what happens in loop 1. Now, we can take this and use it with Faraday's law, which again was in chapter 31. And let's see, let's write out Faraday's law, which looks something like this. This is the induced voltage over in loop 2 is equal to negative N2 times the rate of change of the magnetic flux. And then we're going to take that thing at the top and plug it into Faraday's law to get an equation for mutual inductance. And I'm taking a little bit of extra time to do this particular slide because of the application, which I'll tell you right at the end. Okay? So let's take this top equation and plug this in, solving this for the magnetic flux. So then I have minus N2, and then we've got this derivative with respect to time. And let's see, if I solve that for that, it's going to be M21 I1 over N2. M is a constant, N is a constant, so the N's are going to cancel out, which leaves me with something that looks like this, minus M21 times the rate of change of current. And then we need to step back and look at this equation for a second. So this thing on the left, this is the voltage that's induced in loop 2. And again, induced means that we didn't directly generate it by connecting it to a power source. It means it came as a result of another loop of wire just being in proximity. The voltage induced in loop 2 comes from changing current in loop 1. Okay, so notice those two different subscripts. The 1 going with the current over in loop 1. The 2 goes with the voltage over in loop 2. And by the way, you can reverse all the subscripts, just flip all the way around. The 1s and the 2s, flip them around, because this thing would work exactly in reverse as well. If I were to put the current into loop coil 2, I would induce a voltage over in coil 1. There's no reason why 1 is special. So you could flip all of these subscripts around and exactly the reverse is true as well. Here's the thing. I'm guessing that whether you know it or not, you own this apparatus. At least many of you do, and maybe you haven't recognized that you own this apparatus. If you are using an iPhone 8 or newer, or many Android phones that go back even older, anybody have a Palm Pre back in 2009? You're like, no, we were 11 or whatever it was then, okay? Yeah, it had this as well. Wireless charging, which by wireless we literally mean you don't plug the cable in, you just lay it on a platform or bring it really close to a platform. This is the technology that's used for that. If you wanted to rip your phone apart, right, take the back of the phone off, and look right inside the back there somewhere, you're going to find a coil of wire. It's going to be a coil of wire that's, well, not really spread out like that, but like really, really flattened. But still, it'll be a coil of wire that sort of coils in on itself like so, right? If you have a wireless charging pad at home and you take that little brick apart and look inside, you're going to find a coil of wire, okay? And it's going to look almost identical. That one at home, you plug it into a power outlet. That's basically what might be coil 1. Passing through that coil, coming from the outlet in the wall, is a current. It's an alternating current, so the current's like always changing. Changing current, that's what we see in this equation right here, okay? If there's a changing current and I have another coil of wire nearby, meaning I take my phone and I bring it typically within, a couple of centimeters of that coil, and you'll feel like maybe a vibration or something, a light will light up, something telling you like, I've detected your phone. Well, that's because the coil in your phone is now near that coil, and all of a sudden it experiences that changing magnetic field that's passing through it, and current begins to flow in the coil in your phone, just like as if I plugged it into the wall itself. So over a short distance, magic happens, which is kind of fantastic. And I've heard, it seems like it's like 50-50. Half the people are kind of like, ugh, what do you mean wireless charging? I have to plug it into the wall. Like, who in the world cares if I do this, or if I plug a cable in? Use it for a week. And you'd be kind of surprised, like there's something about, a difference between being like, I need to charge my phone, and I need to charge my phone. You do that and just add up that little 3-second interaction over the period of a week, and then a month, and then a year, and then all of a sudden you go back and you'll be like, where's my wireless charger thing? And you're like, oh, I really appreciated that. That was kind of nice. That took one little minor stress out of the day that you go through a couple, 3 times, and all of a sudden it's kind of nice. Now, where is this going in the future? Yeah,
So I saw this device called the mother box.
The mother box.
Yeah, and supposedly it's supposed
worried.
to charge your phone from across the room. There's a receiver that you plug into your phone, like a case sort of thing. And
Where'd you see it?
it was on Kickstarter, but they've already got their prototypes out and it works.
Yeah, for several years now, people have been working on this. Nothing's made it to market yet, but sounds like they're trying. There's a bunch of companies out there that are trying to do something like this over longer distances.
Would it just be a stronger current?
That starts to raise some questions, right?
Yeah.
Do you want to walk in between those two coils if it's transmitting at that? I don't know. You got a question or comment?
Comment.
Comment.
I think they're using beam diode power.
Say again?
Beam diode infrared.
Oh, infrared.
Yeah. It has direct infrared towards photoresistors.
Yeah, so then we're talking about something very different. Needless to say, there's a bunch of companies out there that are trying to do wireless charging over distance. Ideally, there's a future where we would just like walk into the building and all of our stuff would just be charging. Which sounds fantastic, but it'd be like Wi-Fi we have for data about Wi-Fi for charging, but eventually we may get there. Yeah.
Is that how Tesla coils work?
Didn't you ask that question last week? No? I feel like someone else was just like randomly. Tesla coil? Maybe that was a different class. I don't know. Related, but a different application. So anyway, this is kind of cool. Go buy a wireless charging pad. If your phone is new enough or supports it and you've been like, I don't want to spend $30, just spend the $30. Trust me, you will enjoy it. And the next thing you know, you'll be like, I need one in my car, and I need one in like 4 places in my house, and like just wherever I am, I just want, let's just throw the phone down, and then everything is happy all the time. It's kind of fantastic. So, enough about that. Moving on to the next page. We had mutual inductance. Now we're going to talk about something called self-inductance. Here's the thing. In chapter 31, there was something called Lenz's law, which basically said that anytime magnetic flux is changing, basically nature itself doesn't like that, and it opposes that change. So if I have a loop of wire, and all of a sudden I bring a magnet closer and closer and closer so that more magnetic field is passing through that loop of wire, the loop of wire itself creates its own current and its own magnetic field to try to say, no thank you to this increased magnetic field. I would prefer if you didn't increase the magnetic field, and I'm going to try to hold you back. Now, it loses. It loses every single time. But it puts up resistance for a little while. It opposes a change in magnetic field. So it turns out that we can take a little loop of wire and put it into a circuit. Everything else up here should look familiar. This little loop of wire is something that we call an inductor. And we already know that if I pass current through a wire and I form that wire into a loop, that we get a magnetic field that sort of like goes right down the middle of it. Remember, we can use the right-hand rule and put our fingers in the direction of the loop of wire, and our thumb points in the direction of the magnetic field that's passing right down the middle. And they've illustrated that here. So as soon as current is going through there, magnetic field and magnetic flux is passing through that coiled wire. The thing about an inductor is that not only does it dislike if like a magnetic field from somewhere else comes along and tries to go through the center of it, it'll oppose that. But even if it creates the magnetic field itself, it doesn't like it, which seems a little bit strange. It's like, you did this to yourself. Like, why are you putting up such opposition? So it's like, as soon as I turn this current on, current begins to flow, the coil itself begins to produce a magnetic field, and then it's like surprised, like, where is this magnetic field coming from? I don't like this. And immediately it fights it. It tries everything it can to try to essentially like oppose that magnetic field and keep it from forming, which seems a little bit weird. In other words, it induces within itself a magnetic field that's in the opposite direction in an effort to cancel it out. Once again, it's going to fail. It can't keep this up forever because notice, I've got this thing connected to a battery. Current is coming. This little loop of wire can't stop it. All it can do is be like, fine, and then it loses, okay? So what's happening here is kind of strange if you think about it. Oh, hello. How are you? Got a question? Okay, sounds good. Perfect. All kinds of things are going on. Isn't it fantastic? You're just like, talking to invisible people. And
So it like moves.
yeah, maybe other people are just going to come and invade our classroom. I don't know. So the thing is about an inductor, it's just wire. There's nothing special about wire. It's wire that I literally took and just went and formed into a little loop. Nothing fancy about that. And yet, when you do that, it seems to, in a way, take on a life of its own. It's like it has an attitude. It's like it likes the status quo. Okay? So when it starts and there's no current in it and no magnetic field, that's the way it wants things to be forever. As soon as you turn on the current and it starts creating a magnetic field, it doesn't like the changes that are occurring within itself, and it will try to oppose it. All right? Just keep in mind, there's nothing magical about it. It's simply a coil of wire. So what happens after some period of time is like this thing turns on its current, it fights it for a little while, and then eventually it's like, I can't fight anymore, and the current that's passing through just passes through, because at the end of the day, this is just a piece of wire. It's not a resistor, there's no opposition, there's no anything, all right? So there's like a period of time where it puts up opposition, then it loses, and then current just flows freely. Do we have kind of the idea so far? Okay, maybe a little bit, all right? Let me give you a couple of equations. First of all, self-inductance. This is, again, the induced voltage is equal to minus L times the rate of change of current. Minus L times the rate of change of current. This L is simply known as the inductance. And the inductance, I think, has the best unit of any unit we get to enjoy all semester. It is the Henry, which is just a name, but it's a first name often. And often I like the fact that inductance is small. So you're dealing with things like microhenries and millihenries. And I just get this vision of like little dudes named Henry wandering about. Like there's 100 millihenries. And I just can't help but see that. Stop the little millihenries. Why are they running about? I don't know. But inductance in henries, it amuses me every time. So just deal with my amusement. You'll be fine. All right. So let's see some things we can do with this. Let's see. We're going to put inductors in circuits like we did with capacitors and resistors and all the other stuff. The key takeaway is just remember that inductors are opposing a change in current. They're opposing a change in current. Before we get to that, I should give you a couple of equations on this. You can see the next slide is RL circuits. We'll get there in just a second. Just a bit of an aside. It turns out that inductors do store some energy. Just like we had capacitors storing energy. Inductors and capacitors store energy. Oh, you can't get back in that way, can you? My apologies. Bye. This is fun for all of us, I think. Except maybe him. I'm sorry. Capacitors and inductors store energy. So when we talked about capacitors, we said U is equal to 1/2 CV squared. We have a similar equation for inductors that's equal to 1/2 LI squared. So the inductance times the amount of current that's passing through squared. There is another way of thinking about this, and this is something I want to just point out because in 2 chapters I'm going to bring it up again. Okay? Inductors store energy, and the way they store it is that it is stored in the magnetic field that's inside them. That magnetic field that's being created in an effort to like oppose or stop the current is what's storing some energy. And it is temporary. Just like with capacitors. Capacitors stored some energy temporarily. And we didn't say it at the time, but you might think of this as being stored in the electric field that's between the 2 plates of the capacitor. So you could think of it in terms of the charge that's on the plate storing energy, or just in the fact that when I separate those charges, it creates an electric field in between. That is storing some energy. But I should point out one other thing
That will also take us 2 chapters from now. And you can say that anywhere there is a magnetic or electric field, there is energy. There's energy in that little region of space where that might be existing. Even without an inductor or a capacitor, if there's an electric field right here, right now, right there at that little point in space, or a magnetic field, there is energy stored in that point in space in the electric or magnetic field. So hang on to that. I'm going to revisit that in chapter 34. Just want to point it out before we talk about inductors some more. But we're going to put an inductor in a circuit with a resistor, much like we did with a capacitor before, and talk about how it behaves. So if I take a battery, this is DC, direct current. I'm just going to turn the current on, and it's going to go, or at least try to. And we turn it on by flipping the switch. You might imagine it's like, yay, current would very much like to flow this direction. But the inductor started with no current in it, and now all of a sudden there is current. It doesn't like that change. So what it's going to do is sort of stall. For a little period of time, there's going to stay no current, but then the current will start to win out, and eventually it'll reach whatever current the maximum possible is in that circuit, okay? So all it does is, instead of the current just immediately jumping to a maximum value and being there if I just had a resistor in the circuit, it sort of just spreads it out in time. It offers some opposition for a period of time and then loses, all right? So what you might say is that here at this instant, as soon as I flip the switch, it's almost like this is an open circuit. It's like I flipped the switch and current still didn't flow because there wasn't a conducting path. It's almost like the inductor is an open circuit. When I get all the way up here to the top, it's like the inductor is what it really is, which is just a wire. In other words, at this point, the current is simply equal to V over R, according to Ohm's law. So it's like it's not even there. It's just a piece of wire. So the inductor is a little strange. It's sort of, it's like it opposes a change, but every instant along the way, it quickly adapts to new situations, okay? So you might imagine, like when this started and there was no current passing through the inductor, it was happy with that, so I tried to put some current in, and it says, no thank you, all right. And like the next instant, it let a little bit of the current through. And if I were to just stop right there, I would have this amount of current, and it would be perfectly okay with that forever, okay? It's only when I try to change it a little more, and you're like, how about we go up to this current? And it's like, nah, okay. And then it sort of gets dragged along to the next current, and so forth. I can stop at any point along the way, and it's just like, okay, as long as you're not changing, I'm happy. This amount of current is totally fine. So what happens when, like, I reach this maximum value and everything is going swimmingly, like the maximum current is flowing, the inductor's like, current! I love current. Current is beautiful, especially this particular amount of current is fantastic. Please don't change it. And then all of a sudden, I decide to, I don't know, maybe like open the switch again, which would stop the flow of current. Well, what it's going to do is be like, please don't take my current away. So it creates its own current for a little period of time. Again, it's kind of a magical device. If you try to increase the current through it, it tries to keep things where it was at lower current. If I try to take current away from it, it'll start making its own current in an effort to keep things the way it was. So if all of a sudden I have this maximum current and I take it away, it'll just be like, no, charges, please keep going. Please keep going around the circuit. But of course, it's just a little loop of wire. It has no particular power in and of itself, which means it can do that for a little bit, but again, it's going to lose. And it'll keep the current going for a little while, but it's going to die out and go to zero, all right? The key is that it opposes whatever change comes its way. Take the current away, it'll make its own. Put current in, it'll try to stop it. You got the basic idea? If you can get that, you can survive this chapter and the next, and life will be okay. So you might expect what happens here is very much like what happened with a capacitor. If I were to look at the current as a function of time, and specifically look at the phase where we are increasing the current, it's going to look a whole lot like what we had before. We're going to have some maximum current times 1 minus e to the minus t over tau. And this time tau is equal to L over R. And this is represented down below by that curve. It's an exponentially increasing amount of current that's reaching some maximum value. And then for this other graph, as we take the current away, so if I say decreasing current, I of t is just equal to I starting, what do we want to call that? I0. So this is our starting current times e to the minus t over tau. And we see that in this curve down on the right. So you might be thinking, why would I want to do this? Why do I want to put something in my circuit that just really doesn't like whatever I tell it to do? Any thoughts? Yeah?
I think an induction point.
Tell me more.
So in order for it to not just try and spontaneously heat up everything at once and do a gradual pass through the circuit.
I hadn't thought about that, but maybe. Yeah, especially since it has the name in it. But but I would be thinking the name could apply a little bit more to a Faraday's law effect than something like this, but maybe. More thoughts? More naps? More ready to go homes? Yeah, a little bit. Okay. What if maybe I have something delicate in the circuit, where the idea of having current just go from 0 straight up to some value could potentially be damaging to those electronics. You might imagine a case where it would be better if it's like, let's just kind of ramp the current up to what it needs to be instead of just being like, bang, current. Okay? So it could be something where we just want to slow that process down. And you can imagine, based on what value of inductance I use in this particular equation, I could make this get there relatively quickly, or we could make this ramp up really slow so that it takes a long time to get to that current, just depending on how delicate perhaps the instruments or the electronics are that's in the circuit. So if we want to just spread things out over time a little bit, we use an inductor because it's temperamental. It has a bit of an attitude and it doesn't like change, okay? That's our RL circuit. Let's do a quick example with this. Actually, I'm going to fill that example in the post lecture. It's like exactly like the capacitor problems, believe it or not. Once I write out the solutions, you'll be like, oh, we've done that before. So I'm not going to take the time to do that. Instead, I'd like to try to be able to finish up this chapter. What happens if I combine, notice at the top there, LC circuit, an inductor, with a capacitor? So notice, no resistance. So we're putting a different combination together here with two things that we've now learned about. Let me point out that the fact that there is no resistance is theoretical. Everything that we put a capacitor and inductor in, there's going to be resistance. If for no other reason than the capacitor itself is some wire, the wire is going to have some resistance, okay? So think of this as theoretical. And we're going to go through a series of steps to kind of give you a feeling for how this works. If you're thinking of something to compare this to, kind of imagine this is like having no friction. Back in Physics 220, we often did problems that we said like, oh, let's go ahead and like solve this problem completely, even though really it was theoretical and couldn't completely exist because actually having no friction is kind of out there, right? We can make the friction really, really, really low, but actually getting rid of it completely is difficult, okay? So that's kind of what's happening when we say we have a circuit that has no resistance. It's like we're pretending there's no friction. So what would happen? Take a look at this. We have a capacitor, we have an inductor. We're going to say that the capacitor is all charged and ready to put charge into the circuit. All I have to do is connect the switch, okay? And we're going to go through a few different steps that's going to happen. So notice step 1 up here. Capacitor is charged initially, and then we're going to close the switch. As soon as I close the switch, what's the first thing that happens? Don't read up there. Don't. I see you, you're all like, just looking at this, where would the charges go? Which direction? All right, they're going to leave the positive side and go around this way. But are they going to be able to do that immediately in like their full capacity? No, because of that inductor at the top, right? It's going to be sitting there being like no current, and then it's like, current, and it's going to stop. And then quickly, it's going to start to kind of allow that current through, all right? It's going to try to oppose it. So in other words, you can see here, current flows, and the inductor is going to oppose that change. So take a quick look down at these graphs on the bottom left. So you can imagine right here at the beginning, we start with all of this charge. Charge begins leaving the capacitor, right? So that amount of charge is going to be dropping all the way down to eventually it's going to be completely discharged at some point. So that's what's represented by this first little bit of the curve. While that's happening, if I look at the amount of current that's passing through the inductor, well, right at the start, we start with none, but then it begins allowing the current to flow. That's exactly like what we saw 2 slides ago on this particular graph, okay? It's just like one little part of the graph now, okay? So it begins to allow the current to flow. The thing is, at some point, this is completely out of charge. Well, that's the point when the current's not going to get any bigger, right? It's like the capacitor's out of charge. It's saying like, I've got nothing left to give the inductor at that point. Which means what's going to try to happen is the capacitor is going to be like, I'm done. No more current. I'm completely out. The inductor is not going to like that either, right? We said that whether you try to put current in or take current away, it's going to oppose the change. Which means that at this point, it's going to be like, fine, I'm just going to keep the charge going on my own, even without you, capacitor. And it's going to try, and notice all of these are positive currents. It's going to try to keep the current going, but it's going to fade away to 0. Do you follow that first little phase? Okay, so the capacitor completely discharges. While it's discharging, the current is allowed to get bigger and bigger and bigger. It reaches a maximum when the capacitor runs out of charge. And at that point, it says, fine, I will keep pushing the charge in the same direction, but it slowly loses that battle. All right? But notice what happened during that second phase. The capacitor was completely discharged at this point, but then the inductor kept pushing charge the same direction. Meaning, all of these positives had gone around and balanced out, so this was completely neutral. But then the inductor said, keep going, charges, meaning that now positives were building up on this side. Notice what's happening here. Charge on capacitor is growing, it's just growing in the negative direction. Kind of makes sense a little bit, okay? So then now the capacitor at this point is completely charged the other way, and then everything stops once again. Notice at that point, we've reached 0 current. So you can imagine now we have capacitor completely fully charged in the opposite direction. So it says, fine, the switch is still closed, it's time to flow the other way. So all the positives that are on this side will be like, I'm going to run around this way, and the inductor is going to be like, no thank you. And then it'll allow the current through, and then this will run out of charge, and the inductor will say, oh no, where's my current going? I'm going to keep pushing the charges, and then it'll recharge the capacitor in the opposite direction. And then, of course, this thing can repeat again and again and again. It's like capacitor charged, and then it's charged the other way, and then it's charged the other way, and then it's charged the other way, and it just keeps happening over and over and over again. Okay? This is illustrated here. All right? This is just going to keep oscillating exactly like that. Capacitor charged in the positive direction, capacitor charged in the negative direction, capacitor charged in the positive direction, and so forth. Current is going to go all one direction, and then it goes the negative direction, then it goes the positive direction, then it goes the negative direction, and so forth, because of this interplay between something that can store charge and something that doesn't like changing current, which in a way is kind of weird and kind of interesting. Okay? So first of all, remember, this thing is theoretical. The idea that I can take a capacitor, put it in a circuit with an inductor, and just stand back, and that thing will just have current going back and forth for all of eternity, well, that clearly can't happen. That would violate some laws, okay? What's really going to happen is that this will sort of, depending on the amount of resistance in the circuit, will sort of like fade away, and it'll eventually die. Like the circuit's probably going to heat up, there's going to be collisions of electrons, it's going to lose energy in some way, and it'll fade out. Yes?
Does that also induce a magnetic field?
Does that also induce a magnetic field in the one coil that's there?
Well, no, because wouldn't it also just be a changing of current just in different directions? So would that then also...
So the inductor itself produces a magnetic field in itself.
Right.
And if I were to put a coil of wire nearby that, then yes. And then there's also the entire circuit that is a loop of wire, which would be generating a magnetic field too. There's a lot of stuff that's going on there at the same time. As soon as I have current that's changing, it's kind of like electromagnetism jumps to the next level, and there's a lot of stuff that's dependent on a lot of other stuff. So we're having to ignore the fact that that's happening. Okay? This should remind you a little bit of something. If you go back to 220, can anybody go back there in your mind, or have you completely forgotten everything that happened in that class? Everything? Every single thing that happened is gone.
Yeah.
I get that. All right? This is not terribly different than the spring and mass system. All right? In the spring and mass system, you would pull the mass back, that stretched the spring, and at that point, there was energy stored in the spring itself. That's kind of like the capacitor having charge that's sitting there ready to go. Let go of the mass, close the switch, the mass begins to speed up, and the charges begin to flow. They're analogous to each other. It's the same thing. At some point, this is completely discharged, and there's all of this maximum current that's flowing through the inductor. That's when the spring isn't stretched anymore, when it's back to the middle point, and it has all of this velocity. It's like the velocity is the current. And then it goes the other way and begins to compress the spring until it reaches a maximum again. That's when the capacitor has recharged in the opposite direction. These things work really, really similar to each other. Okay, spring mass system that oscillates back and forth, or an LC circuit that oscillates back and forth in a way that I can't really see with the charges and the current that are trading with each other. Okay? In other words, this thing has a name. It is known as the LC oscillator. The LC oscillator, which is analogous to the spring mass oscillating system. It turns out that it is oscillating between potential energy stored in the capacitor and kinetic energy in the current that's passing through the inductor. You have potential energy stored in the capacitor, kinetic energy that's in the current that's passing through the inductor. And those are oscillating between each other because you can see something like this. We go from all of the energy being stored in the capacitor, it drops as the current increases, and then I have nothing stored on the capacitor and I have maximum current, and then it goes the other way once again. You have these two forms of energy that are going back and forth. Okay? Are we still doing okay? You're like, we weren't doing okay when we stepped into the room and picked up our exam. So like I told a few people, I think what we should do is that any exams that weren't picked up, we're just going to sprinkle all those points over the people who are here, right?
Yeah.
So all of these points go to 0, and then you all get additional points. That sounds fair, right?
I agree.
That sounds fantastic. So we should have like another rush to the front for everybody to pick a second exam that you want to add to your score. Wow, I can't even imagine how much trouble I'd get in. I should just like leave and never return to this campus because someone would destroy me, I'm sure. And their names are, I could just read them off because there'd be a lot of angry people. I'd be very unhappy. All right. So let's take this the next step. Notice now it says RLC circuit. Okay. So now we're actually going to put the resistor in with the capacitor and the inductor. So now we have all three that are in there. And notice again, we're saying that it is without a source, meaning that all of the charge is just going to come from a charged capacitor. And then we're going to turn it loose, all right? It turns out that it is essentially what you might think of as a, let's write it this way, as a dying LC oscillator. The resistance essentially acts like friction, and you get what I was describing on that previous slide a little bit, where instead of oscillating perfectly forever, maybe it just sort of fades out and eventually goes to nothing. Okay? You might remember, again, I don't know if you covered this in 220, but what's known as damped oscillations. Does that ring a bell for anyone? Maybe a little bit. Things could be overdamped or underdamped or critically damped, nothing at all. And maybe you saw a graph that looked like that. No, nothing at all. That's totally fine if you didn't learn it. You don't need to know it now. I'm just drawing a comparison between the two. It's basically the idea of depending on how much resistance I put in the circuit, I can make the oscillations go for a little while and die, or I can make them like maybe not even oscillate at all, just be like, oh, blah, and it just like quits oscillating right during the first oscillation. Or I could have something that's kind of in between the two. Depending on how much resistance, I can make the oscillator stop quickly or go for a while, okay? This is kind of like, for those of you who didn't cover damped oscillations, you know, like the shock absorbers in your car, you know, they're attached to the wheel, right? And the idea is for you to hit a bump and it like compresses a spring and the spring goes right back to where it was so that, well, you don't feel the bump, ideally. It's just like your car goes and the spring goes, ooh, and it goes right back to where it was. What you don't want it to do is to be like, woo. So you're like if you ride in a taxi that's been on the road a little too long and its springs aren't working so good anymore, and then it's like you hit a bump and you're like, ee, and then you eventually get sick a few minutes in that car, right? Well, that would be a case where maybe this oscillates a few times and eventually dies out because things aren't working quite the way they should. You also don't want the springs in your car to like not oscillate at all, meaning go back to the middle point. Because imagine if you hit a bump and then your tire goes up and doesn't come all the way back down. That sounds like a problem, right? Because then it's like, boom, and the whole car just falls on its side, all right? Hey, greetings again. Want your phone? Your phone's there. You can trade it for an exam and just put it down there somewhere. You can come for the rest of class or you can just leave. Either way, you're tired now. Yeah, I understand. I should grade it on the spot. No, I wouldn't do that to you. That's just me. Yeah, okay. Yeah, it's not going to happen. All right, so the car, the oscillations. This is analogous to something like that. We can make the oscillations go or die out. We're not going to do any problems with that. I just want to point out that it's a thing. that, as you will notice, is the end of chapter 32. What I want you to do is hang on to this little idea all the way to the end of chapter 33, where we're going to revisit it. I can't talk about it now because there's like a bunch of things we have to kind of learn before we get there. Okay? Does anybody have any questions about anything in 32? You'll notice there wasn't a lot of like heavy problem solving, these sort of things there. It was mostly conceptual, maybe some smallish kind of problem stuff. Look in the homework to get an idea of stuff that I could ask, but it's not a lot of like crazy heavy Gauss's law kind of stuff. Everybody's favorite, right? Let me get started just a little bit with chapter 33. We've got a few minutes left, and like I said, there's only like, since I'm getting rid of a couple of them, 5 slides. We might be able to do 5 slides. I don't know, all right? This is going to bring us a little closer to reality. Like everything we've been talking about is direct current, meaning we turn the current on, and there it is. Okay, the only variations we've seen in that is when I put an inductor in the way, I can kind of oppose it and make it vary a little bit over some time. Or if I put a capacitor in the circuit, I can make some interesting things happen with that direct current as well, right? What we're going to talk about now is what's known as alternating current. Alternating current is what's actually coming out of these wall outlets over here. AC is alternating current. So you can see the symbol here that we use for alternating current. So instead of a battery, our source is just going to be something that's alternating, that's causing the current to fluctuate, to go up and down and up and down and up and down. And in this first particular case, we're just going to connect it to a resistor. This is going to be instructive in some part because it's going to tell us a little bit about how alternating current behaves. So we're going to learn a little bit about AC itself here. And then we're going to put it in a circuit with a capacitor and see what happens. And then put it in a circuit with an inductor and see what happens. And then I'm going to tell you an application of that stuff. And then we're going to put it in a circuit with all 3, which is basically this entire chapter. Okay, we're not going to do that. That involves, well, some ridiculous looking stuff. I don't know if you agree or not. And we will talk a little bit about that last slide. All right, so it turns out, actually, we don't need that slide either. All right, so let's start with the resistor. Just a resistor connected to alternating current. So you can see over here on the right, this is the voltage that you would detect if you just monitor what's coming out of one of these outlets. The voltage goes from being 0 up to some maximum in a positive direction, and then it ramps itself down to be a maximum in the negative direction and oscillates back and forth like that as a function of time. And it's doing it really rapidly. It's going through one of these oscillations about every 60th of a second. Okay, so 60 times a second, it goes through this oscillation all the way back up and back down. All right. When we do that, you can imagine that that's going to cause a change in how much current goes through the circuit and through the resistor. It turns out that if I only have a resistor in the circuit, the current responds just like you might expect it would with the voltage. So when I have no voltage being applied, there's no current in the circuit. Well, that's a big surprise. When I have a maximum amount of voltage being applied, at that point in time, I have the most current, and so forth, okay? As I apply a voltage to the circuit, the amount of current that's flowing through the circuit and hence through the resistor is varying exactly the same, okay? The peaks are together, the valleys are together, the 0 points are together, and everything in between. So we could say that as long as I have just a resistor in the circuit, we could say that the applied voltage and the resulting current are what we call in phase. They are at the same point in their oscillation together at every point in time. Question in the back.
Is the only difference between the two just the value of the resistance from voltage to current? Like that would just be the amplitude difference?
Basically, yeah. Take the top one, divide by the current by the resistance, and you should get the bottom curve. Yep, just according to Ohm's law. So if we were to write some of that out just a little bit, let me see what I want to say here. Let's say that first of all, we have this applied voltage. So V is equal to I times R. And it turns out that that I is going up and down according to this function, cosine of omega t. And I0 is the peak current, the most you ever have. And that's times R. And then I times R is also V, so we could rewrite that one more time as V0, the peak voltage, times the cosine of omega t. All right, so that tells you something about what value you have at different points in time, and it's always changing, both magnitude and over a period of time also changing direction, right? So you might start to get the idea that if I'm going to have something like this that's always changing in magnitude and direction, that stuff we learned about in the previous chapter and the chapter before is going to come into play, because I have stuff like inductors that don't like all that change. I can put capacitors in the circuit, and now all of a sudden capacitors are like getting charged and discharged like really, really rapidly as the current goes back and forth. So interesting things are going to happen when I have something like this, which is alternating back and forth all the time. Before we go to the next slide, let me point one thing out, is that it's a little hard to like report what kind of voltage you're using or how much voltage. For instance, if you look at this and you're just like, hey, what's the voltage if I connect something to the wall outlet? How much voltage is there? You'd be like, well, it's all of these values. Well, that's not terribly helpful. So you might say, well, tell me what the average is. Well, it looks a whole lot like the average is 0, right? Same amount positive and negative, so the average voltage is 0. So it's like, those are two possible answers. Like, how much voltage is there if I connect something to the wall outlet? Well, it's like a bunch of different values, or if you want the average, it's 0. Neither one of those numbers or answers is terribly helpful, okay? So there's two different things that are typically reported. You can use these peak values, okay? So a peak value is something that might be useful. And that's just the amplitude. It's the maximum it ever gets to. That's one option. Or you can use what's known as RMS values. And that's typically what you would see printed on the back of a device or on an outlet, is the RMS value, which isn't exactly an average, but it's kind of close to it, and that's about all you need to know. In fact, it is literally 3 mathematical operations. It's square, so just take all the values and square them, which gets rid of the negatives, and then take the average, which is the mean, and then take a square root because I squared all that stuff to begin with. It turns out it's a way to take things that are fluctuating between positives and negatives and giving me some kind of a positive average value, but it doesn't really work exactly the same as an average. So it turns out if you work that through, VRMS is equal to the peak value over the square root of 2, and IRMS is equal to the peak current over the square root of 2, and I'm so out of room down there. Let me zoom in so you can see what I just wrote. Peak values divided by the square root of 2 is this thing known as the RMS value. Should I make it bigger? Is that too much? It won't get any bigger than that. All right, so the key takeaway from this slide, resistors, they behave perfectly normally when I put them with alternating current passing through. Nothing weird, nothing odd, nothing strange. They offer exactly the same amount of resistance to alternating current that they did to direct current, okay? Resistors are not strange at all. The problem is when I get to something like capacitors and I start to think about what they're doing, and I'm going to talk about this slide and then we'll be done for the day. So think a little bit about what's happening with the capacitor when I connect it to alternating current. You might imagine that for starters, it's like, ooh, I'm going to send some charge this direction. But almost as soon as I do that, it's like, no, never mind. I'm going to ramp that down and send charge the other direction. And as soon as I've done that, it's like, nah, never mind, I'm going to send the charge the opposite direction. But I'm making that change 60 times every second. The capacitor never really even has a chance to like fully charge. It's more just like, hey, I'll take some charge. Never mind, I'll give the charge. Hey, I'll take some charge. Never mind, I'll give the charge back. In fact, it's almost like the capacitor isn't even there in a way. If I try to send current directly through a capacitor is literally a break in the circuit. Well, it'll fill up on one side and then the current just stops because it has nowhere to go. All I can do is charge the capacitor. If I have alternating current, well, it's like that break doesn't really matter so much because it's like I'm going to send the charge one way and partially charge the capacitor and then just flip it the other way. It's kind of like I'm sort of avoiding the capacitor in a way, right? It's like I know there's a break here, so let's just like kind of go that far and just sort of stop, all right? It's more like I'm just sort of sloshing charge back and forth in the circuit and avoiding the fact that there's a break in the circuit there at all. So a capacitor behaves a little bit weird in an alternating current. If I take a look over here at this graph, let me see which one I want to look at. Let's start at this point. Right? And let's say that this is t equals 0. And let's think a little bit about what's going to happen. Well, the current is what I'm applying to the circuit. So maybe we start with no current and then begin ramping the current up. And now as I think about it a little more, that's actually not the point that I wanted you to focus on. So let's go here. Let's go to this point. This one's better. And it all just repeats, so it really doesn't matter, but that's the talking point I wanted to begin with. So I start by saying like, go current, yay. Current's going, and immediately the current begins ramping down because it's oscillating. It's current that's varying, it's alternating current. While that's happening, the charge and therefore the voltage on the capacitor is growing, all right? It stops growing as soon as the current gets to 0 and starts going the opposite direction. So it's like as long as the current is a positive value, I'm getting positive charge on the capacitor. As soon as the current becomes a negative value, I start taking charge off and I begin charging it the opposite direction, okay? So you can see that if I look at the green curve, think of the green curve as the applied current or the current I'm trying to put through the circuit. And I think that's a brown curve as the voltage across the capacitor. And you will notice that they do not peak at the same time, which I think makes some sense because if there's no charge or voltage on the capacitor, well then if I start passing current, it takes a little bit of time for that voltage to build up as charge begins to grow on the capacitor. So if I start with none and start sending charge that way in the positive direction, a little bit later, it'll reach a peak in voltage. And then when I start sending current the other way, I'm starting to pull charge off the capacitor, which means the voltage ramps down, and so forth. The thing is that there's always this lag between the two. That current and that voltage don't happen at the same time like they did with the resistor, because the capacitor has this sort of delay, okay? In other words, we can say that these two things, the voltage across the capacitor, we would say leads the applied current by 1/4 of a cycle. By 1/4 of a cycle, or sometimes that's just called 90 degrees, or you could call that pi over 2 radians. All of those represent a fourth of a complete oscillation. VC is leading, excuse me, I said that backwards, didn't I? You know why? Because I'm on the wrong piece of notes here. They're out of order. Let's flip that around. I leads the resulting voltage. Now everything is messed up. Applied current leads the resulting voltage. My apologies. Why are my notes out of order? That's what I get for not thinking and just rehashing what I see in front of me. Okay, so I apply a voltage and VC follows a fourth of a cycle out of phase. So we could also put one other note here and say that I and VC are out of phase by 90 degrees. Okay, they do not happen at the same time. There is more to be said about capacitors, it turns out, but we'll do that and inductors and wrap up all the material on Thursday. Yay, that'll be the end of it all. All is lost at that point. There is no more. Except Physics 240, which I'm sure everyone wants to take and or is looking forward to. If you did get your exam, come grab it. Otherwise, I'm going to burn it because you didn't really want it. Yeah, what's up?
Are you gonna do it now?
It takes too long. So I'll get it back to you on Thursday if that's okay. But I'll post your grade before that.
Can you let me know?
I'll let you know as soon as it's posted. And also I'll be posting the answer key so you'll look and you'll be like, oh, I know what I did wrong. Okay.
Thanks, sir.
Yeah, you're welcome.